Hello, my name is Steve Bowler, and welcome to the Juniper Border Gateway Protocol BGP Lab number 7. In this lab, we're going to take a look at the BGP attribute known as the local preference. We're going to show you how you can set up the local preference within your BGP configuration, how you would properly use it, when you would want to use it, and why you would want to use it. We're going to also show you some show commands for verification, and we're going to do some trace routes as well. So if this network topology and network diagram look familiar, that is because we used the same network topology and diagram in our BGP labs 5 and 6. So if this is new to you and this is your first time seeing this network diagram, I'm going to go ahead and do a brief summary. We are using logical systems, and then we are connecting all of these routers together via logical tunnels. We have 6 routers in this network topology: router 1, 2, 3, 4, 5, and 6. If you're not familiar with logical systems, I would suggest that you watch my logical systems Juniper labs to get a good solid foundation on how they work. Logical systems allow you to, within one physical Juniper router, break it up into virtual routers, and what we can do is, what I'm doing for training purposes is I'm going to run BGP, and I have a network here, so it allows you to run routing protocols between your logical systems, and then you're going to connect your logical systems together with logical tunnels. So logical systems are really cool. They're kind of like having virtual routers within one physical Juniper router. We're using the logical tunnel interface to connect logical systems. You can also use the EM interface option as well. And all of our logical tunnel interfaces in this network diagram are represented by LT120.XX. For instance, on router 6, the connection between router 6 and router 4 is LT-120.64. The IP addressing is as follows. Router 1 is, for all of its interfaces, are the .1s. Router 3 is the .3s. Router 5 is the .5s, and so on. We have loopbacks on router 6 and router 1. Router 6 is loopback 0.6, in which we have assigned the 6 and 66 networks, both of those /24s, and router 1 is loopback 0.1 with the 1 and 11 network, both of those /24s as well. We are running no IGPs, our interior gateway protocols. This is strictly BGP. And we have router 1 as the route reflector in Autonomous System 100. Also in Autonomous System 100 with router 1 is router 2 and router 3. They are not directly connected, and they do not peer with each other via iBGP, and so that is why we are using router 1 as the route reflector. If you're not familiar with route reflectors and how they work, I have a video that explains route reflectors. At a very high level overview of route reflectors, they allow you to not follow the default rule of iBGP, which is that all BGP speaking routers within one autonomous system must peer to each other to create a full mesh. So that is not taking place in this lab. We have router 1, which is the route reflector that's going to reflect the routes between router 2 and router 3. Same thing for router 6. It's acting as a route reflector between router 4 and router 5 in Autonomous System 200. So our iBGP connections are from 4 to 6, from 5 to 6, from router 1 to 2, and from router 1 to 3. We are running external BGP between router 2 and router 4, and between router 3 and router 5. Our networks are the 12 network between router 1 and 2, 13 network between router 1 and 3, 24 network between router 2 and 4, 35 network between 3 and 5, 46 network between 4 and 6, and 56 network between router 5 and 6. The last thing we're doing is we are exporting our loopback interfaces into BGP on R6 and R1. So on R6, those two networks are coming in, and router 4 and router 5 are both advertising those to router 1, and so is router 1. Loopback 0.1 is being exported into BGP, and router 1 sending it to router 2 and 3, and those are being advertised to router 4 and 5 via external BGP. So let's start off by going over the basics of local preference. This BGP attribute is used to direct traffic within your autonomous system and how it leaves your autonomous system. For instance, within autonomous system 100, the local preference can be set on router 2 and router 3, and this will affect how the traffic and networks off of router 1 leave autonomous system 100 and go to autonomous system 200. It is also important to understand that local preference is the determining factor on the best local preference is the highest value advertised, and that local preference is advertised to all IBGP neighbors. So what you see is that, for instance, if the link between router 2 and router 4 is a more preferred path and has, say, a higher bandwidth instead of router 3 to router 5, a lot of companies use local preference between IBGP within their IBGP configuration to prefer a specific route to leave their autonomous system, or a specific path. You can also use it to do load balancing, and we're going to do that later on in this lab. We're going to show you a couple of different ways you can set up local preference. The default local preference value is 100, and like I was telling you earlier, a higher local preference is preferred. And we should not get local preference mixed up with route preference. Local preference is strictly within BGP and is a BGP attribute, whereas the route preference is routing protocol information needed to pick the best path based on the routing protocols. For instance, on R1, if we are receiving routes from different routing protocols, all with the same subnet mask, the best route preference is going to be preferred based on the route that comes in with the lower route preference. And that's between routing protocols. You can also do static, directly connected, and so on and so forth. So we don't want to get those confused. Route preference and local preference are not the same thing. Local preference is specifically within BGP, whereas route preference is picked by the local router to get the best path via the routing protocol with the lower route preference, or if it's directly connected. So let's go ahead and go on to router 1 and get started. We should be seeing the 6 and 66 networks coming in to router 1. Let's do a couple show commands to show the routes coming in to router 1 and before we change the local preference. So if we do a show route protocol BGP, you can see that we have a local preference value, the default local preference value of 100 for these routes coming in from both router 2 and router 3. R1, if we do a trace route to the 6 network, we'll source it from the 1 network. We can see that the path is from router 2 to router 4 to the 6. If we trace to the 66 network, we should see the same traffic flow, and we do, going from the 12 network to the 24 to the 6, to router 6. Let's do a couple more show commands. We'll do show route receive protocol BGP on router 2, which is the 12.12.12.2. See the local preference of 100 as default. If we look at the connection on R3, we see the same thing. The path is being preferred through router 2 right now. Let's go ahead and do a show route 6.6.6.0/24 detail. We can see the winning factor why router 3 is not being chosen as the best path is because of the router ID. So say we want to manipulate the way AS100 gets to the 6 and 66 networks in AS200. We want to, right now that traffic is going from R1 to R2 to router 4 to router 6. So let's say we want to change this to the path from R1 to R3 to R5 to R6. We can do this by sending a higher local preference on R3. Anything over 100, in this lab we'll just set it to 2000 for those networks. And then we're going to send it to our iBGP, our internal BGP peers. So this is done on router 3. So the simplest way to change the local preference, we can set it for the whole group, the whole iBGP group. We'll do edit protocols BGP. We do a show. We see the group iBGP in which we are peering with R1. We can set the local preference by doing the command set group iBGP. And if I do a space question mark, we can find the local preference option. So we'll go ahead and do that, local preference. If we do a space question mark, it's going to ask us for that value. So we'll do anything over 100, we'll just do 2000 and commit this change on router 3. If we go back to router 1 and do a show route protocol BGP, the path that we're seeing for the 6 and 66 networks has changed to router 3. See the local preference that router 1 is now receiving is 2000. So router 1 now has to make a decision based on local preference. It's seen a local preference for these routes from router 2 with 100, and then it's also seen the local preference value of 2000 from router 3 for these routes. So obviously the higher local preference is going to be preferred, and that's what we are seeing that is taking place. On R1, if we do a show route receive protocol BGP on our router 3 connection, the local preference of 2000 is now being received for both of these prefixes, and the asterisk indicates that that is the best path. If we do a show route receive protocol BGP on our connection to router 2, the local preference is 100, and those routes are not the best. Let's go ahead and do a show route on the 6th network we'll do is show route detail. Shows us the next hop is router 3. And the path through router 2 is inactive, and the inactive reason is because of the local preference. Obviously, local preference of 2000 is winning over the local preference of 100. Let's go ahead and trace. On R1, we'll do trace 6.6.6.6, source 1.1.1.1. We see the path now going from 13 to 35 to 6. So to reach the 6 network, sourcing it from the 1 network, we're going router 1 to router 3, which is the 13 network, then router 3 to router 5, which is the 35 network, and then to router 6. We should see the same activity for the 66 network. Let's go ahead and do that. And that is exactly what we are seeing. So the same path for both routes. We have successfully changed the traffic flow within Autonomous System 100 to prefer router 3 over router 2. So let's say now, for our next example, we want to load balance traffic exiting our local AS, which is 100, using the local preference. We're going to accomplish this by creating a simple routing policy on R2 to set the 6 network with a higher local preference, 5000 in this case, specifically for this network only, and advertise just 100 for the 66 network. So if we review what we did, we went on to router 3. We didn't have to do any routing policy yet. What we did is we just set the local preference under our IBGP group to 2000. And all the routes are now being advertised with 2000 to router 1. What we're going to do now is we're going to go to router 2, and we're going to use a routing policy to manipulate the local preference and create some load balancing, some simple load balancing. We're going to do the command edit policy options, policy statement. Let's call this local pref. This is our routing policy name. We're going to set our term. We'll do set term 1 from route filter 6.6.6.0/24 exact. So we're going to perform an exact match on the subnet mask on this network. So this is our match statement, and our action within term 1 is going to be to then, if we look, do a space question mark, we have the local preference option. We'll do then local preference 5000. Let's go ahead and commit that. The last thing that we have to do on router 2 is export this routing policy into IBGP. So we'll go under Edit Protocols BGP. We'll do a show just to show you what's going on. In our BGP configuration on router 2, we have the group IBGP, which is internal, peering to router 1. So what we're going to do is we're going to do set group IBGP export, and then we're just going to add the name, or we're going to put in the name of our routing policy, which is local preference, our local _ pref. Let's go ahead and commit that on router 2. Make sure it's complete, and it did complete. We go back to router 1, do a show route protocol BGP. What we can see is that for the 6 network, the best path is now going to router 2, whereas the 66 network is still preferring router 3. We do a show route received protocol BGP towards router 2. The asterisk is next to the 6 network. This means that this is the active best path to reach this subnet. The local preference has now been changed to 5000. Whereas if we do a show route receive protocol BGP 13.13.13.3, for our next hop to router 3, the 6 network is not being selected because the local preference value is lower. So we're seeing a local preference now being advertised to router 1 from router 3 as 2000, and then we're also seeing from router 2 a local preference of 5000 for this network. So what router 1 has to do in this case is make the decision of either 2000 or 5000, and it's going with 5000. Let's go ahead and perform our trace routes. We'll do trace route to the 6 network first, source it from 1.1.1.1. The traffic flow is for the 12 network to the 24 network. So obviously the path that router 1 is taking to reach the 6 network is router 1 to router 2, then router 2 to router 4, and then from router 4 to router 6. However, if we do a trace to the 66 network, source it from the 11 network, the path that we are taking on R1 to get to the 66 network is through router 3, router 5. You can see 1335, that's between R1 and R3, and then the 35 network between router 3 to router 5. Let's go ahead on router 1, we'll do a show route on the 6 network. We'll do a show route detail. We're seeing router 3 is not being set as the active best path. It's inactive because of local preference. We're seeing a local preference of 2000 for router 3, and then we're seeing a local preference of 5000 from router 2. One last thing I wanted to show you is that if we go to router 2 and cause an outage between router 2 and router 1, let's do this. We'll go to the top of the config. We'll do set interfaces LT120.21 disable. We'll commit that. What we should see is that all the traffic is going to reroute to router 3. Now we can see router 3 is being chosen as the best path to reach both networks. If we do a show BGP summary, we should see the link to router 2 is active because we just disabled the interface. And now our trace for both the networks are taking the path through router 3. So I just wanted to show you that. None of our traffic is being black-holed or any of that bad stuff that might happen. So to wrap up this lab, we showed you how to set the local preference for all routes on router 3. We go back to router 3. We set the local preference under the group IBGP to 2000. And then we showed you on router 2 how to add the route preference to specific networks, in this case the 6 network, with a simple routing policy. Why you would do this, and that would be for load balancing and other reasons, for reachability off of certain networks. We do a show on R2. We created our simple routing policy that matched the 6 network, and then once that match was made, we set the local preference only to the 6 network to 5000. All other networks were being advertised with the default local preference value of 100 to router 1. So remember that the local preference is going to affect the way traffic leaves your autonomous system, and that local preference is sent to iBGP neighbors as we saw in this lab. So thanks for watching, and